Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is RC filters. Our objective is to examine the frequency response of passive RC filters on an introductory level. As I began the series resonance lecture, let me remind you that it is often said, never try to wrestle a pig. Not only will you get dirty, the pig will enjoy it. In the spirit, I do not intend to take the topic of RC filters to the mat, but rather strike it viciously over the head with a long-handled coal shovel and walk away. As such, this lecture will present only the most important properties of filters and will intentionally avoid any entanglement with the dirtier aspects of filters. If you are looking to get dirty, this is not the time nor the place. The idea is to present filters in a clean, focused, and direct manner, and walk out of this lecture without a spot on us. Let us begin. This lecture operates under the presumption the viewer has a basic understanding of logarithms and gain expressed using the units of decibels, as illustrated in the Logarithms and Decibels lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, please take the time to do so now. Additionally, it is presumed the viewer has watched the series Resonance lecture, also available at the Big Bad Tech channel. You'll recall in the Resonance lecture, we learned that source current through a series circuit peaks at the resonant frequency, FR, and inside a specific bandwidth defined by the lower and upper half-power frequencies F1 and F2, the circuit experiences half power or greater. If you want to think of it in this fashion, a series resonant circuit is a type of filter, specifically a band pass filter, whereby frequencies inside a particular band experience more output and frequencies outside this particular band experience less output. The behavior of a band pass filter explains the title and vice versa. Frequencies inside a specific band are passed, hence the name band pass filter. Get it? Other types of filters exist, notably band reject or band stop filters, which are almost the exact opposite of band pass filters, where a band stop filter excludes or rejects frequencies inside a specific band, also defined by an F1 and F2, and they experience less output. Frequencies below F1 experience more output, as do frequencies above F2. As previously, the behavior of a band stop filter explains the title and vice versa. Frequencies inside a specified band are stopped or rejected, hence the name band stop filter. Get it? Two other common filters are known as the low pass and the high pass filter. We'll spend the rest of this lecture examining simple low pass and high pass filters. A low pass filter has one operating point, known as the critical frequency, FC. Frequencies below the critical frequency experience greater output. Frequencies above the critical frequency experience less output. As the name implies, a low-pass filter allows low frequencies to pass and rejects or stops high frequencies. A high-pass filter also has one operating point, also known as the critical frequency, FC, although its behavior is opposite of a low-pass filter. Frequencies below the critical frequency experience less output. Frequencies above the critical frequency experience more output. As the name implies, a high-pass filter rejects low frequencies and allows high frequencies to pass. Electrical filters, like oil filters, air filters, or water filters, exclude something unwanted and allow something desired to pass through. Instead of filtering out physical contaminants, electrical filters instead filter out electrical signals. Signals with certain frequencies are passed onto the output, and others are rejected or stopped. This lecture will take a quick look at both the low-pass and the high-pass filter on an extremely introductory level. Both these filters can be easily constructed using a series combination of two passive elements, a resistor and a capacitor. A low-pass filter is a resistor in series with a capacitor, and output voltage, the property of interest, will be measured across the capacitor. A high-pass filter, in contrast, is a capacitor in series with a resistor, and output voltage, the property of interest, will be measured across the resistor. Yes, theoretically, one can construct low and high-pass filters using inductors, but they're not, because filters employing inductors don't closely match the theoretical expectations because of the internal resistance of real-world inductors negatively affect their performance. Filters employing capacitors more closely match theoretical expectations. As such, we'll limit our discussion to low-pass and high-pass RC filters. Let's take a look at the low-pass filter first. Again, a low-pass filter is a resistor in series with a capacitor, and output voltage, the property of interest, will be measured across the capacitor. The critical frequency Fc is experienced when the magnitude of the resistive complex impedance Zr is equal to the magnitude of the capacitive complex impedance Zc. If you're as mathematically competent as I expect you to be, solving for the critical frequency, given fixed component values, should be well within your reach. Again, the critical frequency FC is experienced when the magnitude of the resistive complex impedance ZR equals the magnitude of the capacitive complex impedance ZC. Note I've ditched the angles because we are not concerned about angles. All we care about is impedance magnitude. I'm well aware that resistors have an impedance angle of 0 degrees and capacitors have an impedance angle of negative 90 degrees. Given fixed resistive and capacitive component values, we're being asked to solve with a critical frequency FC which satisfies this condition. If ZC equals 1 over 2 pi FC and ZR equals R, we're being asked to solve for the variable FC. If you feel you're up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Algebraic manipulation yields FC to be equal to 1 over 2 pi RC. You're free to use this simplified formula or to derive it on an as-needed basis via algebraic manipulation. Importantly, you should be aware that at the critical frequency, the magnitude of ZC equals the magnitude of ZR. Given this is a low-pass filter, we should expect some predictable behavior at frequencies below, at, and above the critical frequency. Consider the following series circuit, consisting of a 100 ohm resistor and a 12 microfarad capacitor. The source Vin has an effective value of 24 volts and an excitation frequency that can be varied from 1 to 1 kilohertz. What's the critical frequency for this particular circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The critical frequency is achieved when the magnitude of ZR equals the magnitude of ZC. FC equals 1 over 2 pi RC. Substituting in our given values, we find FC to equal approximately 132.6 Hz. Let's check our work. The complex impedance of the 100 ohm resistor at 132.6 Hz is 100 ohms at an angle of 0 degrees. At an excitation frequency of 132.6 Hz, the complex impedance of the capacitor will be 100 ohms at an angle of negative 90 degrees. At the critical frequency, the resistor and capacitor do indeed present impedances of equal magnitude. Let's now examine electrical properties within this low-pass filter circuit at the critical frequency. For a low-pass filter, our property of interest, Vout, will be the voltage across the capacitor. If this is a high-pass filter, output voltage, our property of interest, will be read across the resistor. Perhaps the easiest method of solving for output voltage across the capacitor is through the use of the AC voltage divider rule. The AC voltage divider rule set up to solve for Vout demonstrates that Vout will be approximately 17 volts at an angle of negative 45 degrees. An application of Kirchhoff's voltage law demonstrates that the remaining 17 volts at an angle of positive 45 degrees will be dropped across the resistor. You'll note that at the critical frequency, the resistor and capacitor experience equal voltage magnitudes, yet are phase shifted from one another by a relative 90 degrees. This is understandable because each element in this series circuit experiences the same current, and at the critical frequency, the resistor and capacitor present identical impedance magnitudes. Voltage across each component is understandably the same magnitude. You'll note output voltage, in this case voltage across the capacitor, our property of interest at the critical frequency, is the source voltage divided by square root 2 and is phase shifted from it by 45 degrees. This is an identifiable feature of filter circuits at the critical frequency. Again, at the critical frequency, output voltage will be equal to input voltage magnitude divided by square root 2 and will be phase shifted from it by 45 degrees. Before we move on, it's probably worth a moment of your time to copy these results or make a screenshot for later reference. Let's examine the performance of the same circuit at frequency below and above the critical frequency. As an exercise to the viewer, I invite you to solve for the voltage across the capacitor, i.e. our property of interest output voltage at 66.3 Hz and at 265.2 Hz, respectively half and twice the critical frequency. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following results. At the reduced excitation frequency of 66.3 Hz, the 100 ohm resistor still presents an impedance of 100 ohms at an angle of 0 degrees. At the reduced excitation frequency of 66.3 Hz, the 12 microfarad capacitor now presents an increased impedance of 200 ohms at an angle of negative 90 degrees. Capacitive impedance went up. Voltage across the capacitor should go up. An application of the AC voltage divider rule demonstrates that Vout will be approximately 21.5 volts at an angle of negative 26.6 degrees. At the reduced excitation frequency of 66.3 Hz, output voltage, our property of interest, is greater than that experienced at the critical frequency. This matches our expectations of a low-pass filter. frequencies less than the critical frequency experience greater output. Let's now examine the performance of the system at a frequency greater than the critical frequency. If this truly is a low-pass filter, we should expect output voltage to be less. Let's see if this is the case. At the increased excitation frequency of 265.2 Hz, the 100 ohm resistor still presents an impedance of 100 ohms at an angle of 0 degrees. At the increased excitation frequency, the 12 microfarad capacitor now presents a decreased impedance of 50 ohms at an angle of negative 90 degrees. Capacitive impedance went down. Voltage across the capacitor should also go down. An application of the AC voltage divider rule demonstrates that Vout will be approximately 10.7 volts at an angle of negative 63.4 degrees. At the increased excitation frequency, output voltage, or property of interest, is less than that experienced at the critical frequency. This again matches the character of a low-pass filter. Frequencies greater than the critical frequency experience less output. Let's compare and contrast the performance of the system at frequencies less than, at, and at greater than the critical frequency. Granted, we've only got data for 3 operating conditions, but an obvious pattern should be emerging. At frequencies less than the critical frequency, the circuit experiences greater output. At the critical frequency, output voltage is input voltage over square root 2. At frequencies greater than the critical frequency, the circuit experiences less output. This is classic low-pass filter behavior. Frequencies less than the critical frequency experience greater output, and frequencies greater than the critical frequency experience less output. Let's see if these observations hold true for a range of frequencies. As an exercise to the viewer, I invite you to solve for output voltage at the following reduced frequencies: 1/3, 1/4, 1/5, and 1/10 of the critical frequency, as well as the following increased frequencies: 3 times, 4 times, 5 times, and 10 times the critical frequency. Go ahead and pause the lecture and do so now. Just kidding. This is obviously a lot of tedious busy work best suited for a computer. In fact, the analysis of filter circuits is one of the rare occasions in which I find computer simulation to actually be better than a hardware lab, simply because of all the tedious busy work involved. Many software-based circuit simulators offer a frequency sweep or a Bode plotter, where the software simulator varies excitation frequency from a user-defined low to a user-defined high. The simulator then plots the electrical properties of the circuit of interest for the desired frequency range. A plot of output voltage for this low-pass filter might look something like this. It doesn't look as snappy and defined as when I first introduced the low-pass filter. However, the results speak the truth. As we'd expect, at frequencies less than the critical frequency, right about here, the circuit experiences greater output voltage, and at frequencies greater than the critical frequency, the circuit experiences less output. This plot may seem less impressive than I initially led you to believe. Note, however, that I've plotted these results on a graph using a linear horizontal scale from 0 to 1000 Hz. This will work. However, filters often plot output on a semi-log plot, where the vertical Y property, in this case output voltage, is expressed linearly, and the horizontal X frequency scale is expressed logarithmically, where each equal horizontal interval represents a power of 10. The reasons for this are twofold. One, it allows a lot of data to be plotted on a smaller graph, and 2, it introduces a level of math that confounds and frustrates generation after generation of first-year electrical engineering students. Adding a dubiously necessary level of mathematical complexity to the process ensures the unwashed rabble continually hold electrical technicians in high regard. Trust me, if it was easy, everyone would be doing it.